So in this multiplication, right, I think you will be able to understand what's happening, but let me just explain. So what's happening? So what's happening is 4580. So you can think of this axis as the x-axis that is having 4 elements. Right now it is just 3 elements, and this axis, y-axis, has 5 elements, and this is the axis that is the z-axis. Let's think of it that way. So what's happening is he's saying the dot product that's happening, right, is across this array. This array, when I say it's 1 4 7 10, 1 4 7 10 that we see, right, that is 80 in this case. 80 in this case. Ours is like 1 2 3 4, 4 elements that gets multiplied with another torch.random array that is 4 into 80 into 200. Again, you can think of 4 into 200 and then a bias added. So what's happening is the output that we'll get will be 80 elements in here, because these all will be multiplied by that and the bias added. So this will become like a 200. So this will remain 4, this will remain 5, and each of these 1 4 7 10 will get multiplied with the torch.random array plus the bias will get added. So this will become like a huge 200 side. So we will have 200 elements in this, again 200 elements in this, 200 elements in this one, 200 element in that, 200, 200, all of the 200s. Okay.
That case will become 4 by 5 by 200. You can add as many dimensions as you like on the left here. And so effectively what's happening is that the matrix multiplication only works on the last dimension, and the dimensions before it in the input tensor are left unchanged. So that is basically these dimensions on the left are all treated as just a batch dimension. So we can have multiple batch dimensions, and then in parallel over all those dimensions, we are doing the matrix multiplication on the last dimension. So this is quite convenient because we can use that in our network now. Because remember that we have these 8 characters coming in, and we don't want to now flatten all of it out into a large 8-dimensional vector, because we don't want to matrix multiply 80 into a weight matrix multiply immediately. Instead, we want to group these like this. So every consecutive 2 elements, 1 2 and 3 and 4 and 5 and 6 and 7 and 8, all of these should be now basically flattened out and multiplied by a weight matrix. But all of these 4 groups here, we'd like to process in parallel. So it's kind of like a batch dimension that we can introduce. And then we can, in parallel, basically process all of these bigram groups in the 4 batch dimensions of an individual example, and also over the actual batch dimension of the 4 examples in our example here. So let's see how that works. Effectively what we want is, right now, we take a 4 by 80 and multiply it by 80 by 200 in the linear layer. This is what happens. But instead what we want is, we don't want 80 characters or 80 numbers.
So just to understand each of the dimension here, right? We have 4 examples. That's what is mentioned here. We have 4 examples. Each has 8 context words. Okay. Each has 8 context words. Now, each of these words that we are seeing, right, has its own set of embeddings. So that's where 4 into 8 into 100 it becomes. So for examples, for each example we have 8 context words, and each word has then its own embeddings, its own representations. Okay, then we used to flatten the layer, then it used to become 4 into 80. So it's like we are stacking 1 7 4 10, 1 7 4 10, that way. On top of that we are placing 13 16 19 22. So this is sitting on top of means this is there, on top of that we are placing one more. So it's a huge, so it becomes 4 examples, but it this becomes 80. Okay, 8 into 10 of each size, so 80. And final output layer is 4 into. Okay, so this is the logic calculation that's happening. So internally we have um 200 layers. Okay, in the first the input layer, the next is the intermediate layer, which has 200 um, neurons. So that's where 40 4 into 80 into 80 into 200. So it becomes 4 into 200, and then we are, this is the bias, one more that is getting added to all of those neurons.
To come in. We only want 2 characters to come in on the very first layer, and those.
So very, so he's saying first 2 elements to come into the picture. So this becomes, then out of those 4 examples, we'll taking 2 examples. So that will be like I'm just, so 2 layers, each will be multiplied with 80 into 80 into 200. That will branch out to all of them. Torch dot, sorry, it's random 200, but this is just the 2 examples. We need to take the for the other 2 examples, right? So this is the next 2 examples. Okay, because we are taking 4 examples in this, right? Inputting 4 examples, so 2 examples, 2 examples, like that, how they will be working. But this is something we need to see, or what he tells.
2 characters should be fused. So, in other words, we just want 20 to come in, right? 20 numbers would come in.
Uh,
And here, we don't want a 4 by 80 to feed into the linear layer. We actually want these groups of 2 to feed in. So instead of 4 by 80, we want this to be a 4 by 4 by 20. So these are the 4 groups of 2, and each one of them.
okay, it is a bit different in that case. So the output of the layer, we don't want 4 into 200. Let's see this again. Wait.
So 80 should be fused. We only want is here and also by all of these. We want to group these like this. So every consecutive two elements, 1, 2, and 3, and 4, and 5, and 6, and 7, and 8, all of these consecutive want 8 dimensional. So for that, we have these 8 characters coming in.
Oh, okay. So what he's saying, right, is this 8 character itself that are coming, right? The context vectors. I think he wants to. Okay, that's why he's saying bigram. That's what, right? So he's taking this 0, 0, then this 0, 0, then 0, 11, 11, 13, 13 to 218. So like that. So what he's saying is rather than having 8 and 10 stacked on top, right, take 2. So make it 20, 20, 20, 20. That also becomes 80. Okay, that is the first thing.
And we don't want to now flatten all of it out into a large 8-dimensional vector because we don't want to matrix multiply 80 into a weight matrix multiply immediately. Instead, we want to group these like this.
So for each of the example, we will be grouping 2, that is 20, 20, 20, 20, 4 20s. Okay, and obviously, so leave upon. So first is the number of examples. I'm not thinking about it. The next is 4, and 4 are the group of 20 vector sizes. Okay, so this means if there were 8 words here, right, something like this, if you're seeing, right, 8 words here, so we are taking dot d I o like that. Oh, no, 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 that is also not the case actually, because we are taking just 4, right? id io nd re. So like that we are taking just 4 at a time, and the bigrams we are taking. So that's where this becomes 4 into 4 into 20. This becomes 20. So the output will be 4. We can do itself, right? And, and then this became dot shape. Oh, sorry, this should be 20. Sorry. Ah, okay. So what's happening for um 4 that are here, right? Rather than being a 20 size, now it has become a 200 size. Okay.
So every consecutive now basically flattened out and multiplied by a weight matrix. But all of these 4 groups here, we'd like to process in parallel. So it's kind of like a batch dimension that we can introduce. And then we can, in parallel, basically process all of these bigram groups in the 4 batch dimensions of an individual example, and also over the actual batch dimension of the 4 examples in our example here. So let's see how that works. Effectively what we want is, right now, we take a 4 layer, this is what happens. But instead what we want is, we don't want 80 characters or 80 numbers to come in. We only want 2 characters to come in on the very first layer, and those 2 characters should be fused. So in other words, we just, and here we don't want a 4 by, so instead of 4 by 80, these are the 4 groups of 2, and each one of them is 10-dimensional vector. So what we want is now, is we need to change the flatten layer, so it doesn't output a 4 by 80, but it outputs a 4 by 4 by 20, where basically these, every 2 consecutive characters are packed in on the very last dimension, and then these 4 is the first batch dimension, and this 4 is the second batch dimension, referring to the 4 groups inside every one of these examples. And then this will just multiply like this. So this is what we want to get to. So we're going to have to change the linear layer in terms of how many inputs it expects. It shouldn't expect 80, it should just expect 20 numbers. And we have to change our flatten layer so it doesn't just fully flatten out this entire example. It needs to create a 4 by 4 by 20 instead of a 4 by 80. So let's see how this could be implemented. Basically right now we have an input that is a 4 by 8 by 10 that feeds into the flatten layer, and currently the flatten layer just stretches it out. So if you remember the implementation of flatten, it takes our x and it just views it as whatever the batch dimension is, and then -1. So effectively what it does right now is it does e.view of 4, -1, and the shape of this of course is 4 by 80. So that's what currently happens, and we instead want this to be a 4 by 4 by 20, where these consecutive 10-dimensional vectors get concatenated. So you know how in Python you can take a list of range of 10, so we have numbers from 0 to 9, and we can index like this to get all the even parts, and we can also index like starting at 1 and going in steps up to get all the odd parts. So one way to implement this, it would be as follows. We can take E and we can index into it for all the batch elements, and then just even elements in this dimension, so at indexes 0, 2, 4, and 8, and then all the parts here from this last dimension. And this gives us the even characters, and then here this gives us all the odd characters. And basically what we want to do is we want to make sure that these get concatenated in PyTorch, and we want to concatenate these 2 tensors along the second dimension. So this and the shape of it would be 4 by 4 by 20. This is definitely the result we want. We are explicitly grabbing the even parts and the odd parts.
So you won't be able to visualize it usually. So 4 cross 4 cross 10, so what's happening, it is taking, so as I told, right, this is 4 cross 8 and 10 each. Okay, so here it is taking the even one, so 0th one, second one, fourth one, so we have 8 like this here, right? So it is taking the even one, 0, 2, 4, 6, 8. Okay, the other one, now to take the odd ones, right? So that is the odd ones, 1, 3, 5, 7. Now he's saying concatenating in this axis means 1 0 will concatenated with 1, 1 with 2. Okay, so here you are getting 0 2 4 6 8 1 3 5 7. Okay, and you want to concatenate across this means 0 1 2 should sit on top of 0, 3 should sit on top of 1, like that. Okay, so that's where he's doing torch.cat torch.cat
And we're arranging those 4.
Okay, okay, dim equal to 2, sorry. So now what happened is the same thing. 2 has been stacked on top of 0, 3 has been stacked on top of 1, like that. So now we have 4 elements in here, and each of them are size of 20. Means, oh, sorry. 1 is tagged on top of 0. So this gives us the odd, this gives us the index. So 0, 2, 4, 6, and 1, 3, 5, 7. So we are saying first element of this and the element of this. So 1 sits on 0. So that is the bigram. Then 2, 3. 3 sits on top of 2. 2, 3, 4, 5. 5 sits top on 4, like that. So we will just have 4 huge like this, and 20, 20, 20, 20.
4 by 4 by 10 right next to each other and concatenating. So this works, but it turns out that what also works is you can simply use a view again and just request the right shape. And it just so happens that in this case, those vectors will again end up being arranged in exactly the way we want. So in particular, if we take E and we just view it as a 4 by 4 by 20, which is what we want, we can check that this is exactly equal to, let me call this is the explicit concatenation, I suppose. So explicit.shape is 4 by 4 by 20. If you just view it as 4 by 4 by 20, you can check that when you compare it to explicit, you get a big.
Comma 4, comma 20. All 20.
This is element-wise operation, so making sure that all of them are true, values to true. So basically, long story short, we don't need to make an explicit call to concatenate, etc. We can simply take this input tensor to flatten, and we can just view it in whatever way we want. And in particular, we don't want to stretch things out with -1. We want to actually create a 3-dimensional array And depending on how many vectors that are consecutive we want to fuse, like for example 2, then we can just simply ask for this dimension to be 20 and use a -1 here, and PyTorch will figure out how many groups it needs to pack into this additional batch dimension. So let's now go into flatten and implement this. Okay, so I scrolled up here to flatten, and what we'd like to do is we'd like to change it now. So let me create a constructor and take the number of elements that are consecutive that we would like to concatenate now in the last dimension of the output. So here we're just going to remember self.n equals n. And then I want to be careful here because PyTorch actually has a torch.flatten, and its keyword arguments are different and they kind of like function differently. So our flatten is going to start to depart from PyTorch flatten. So let me call it flatten consecutive or something like that, just to make sure that our APIs are about equal. So this basically flattens only some n consecutive elements and puts them into the last dimension. Now here, the shape of x is b by t by c. So let me pop those out into variables. And recall that in our example down below, b was 4, t was 8, and c was 10. Now, instead of doing x.view of b by -1, right, this is what we had before. We want this to be b by -1 by, and basically here we want c times n. That's how many consecutive elements we want.
The reason being that these many numbers we want to concatenate, so this will be 4, 8, 10, because each of the example has 10 context words and each word is 10 in embedding. So 4, 10, 4, 8, 10, we want to concatenate 2 of them. So that's where this is 4. This we are saying we want to concatenate 2, that is coming from here. So c into 2, so that is 10 into 2, 20, and it will try to, means Torch will try to figure out this in place of -1 what it will be.
And here instead of -1, I don't super love the use of -1 because I like to be very explicit so that you get error messages when things don't go according to your expectation. So what do we expect here? We expect this to become t divide n using integer division here. So that's what I expect to happen. And then one more thing I want to do here is, remember previously, all the way in the beginning, n was 3, and basically we're concatenating all the 3 characters that existed there. So we basically concatenated everything. And so sometimes that can create a spurious dimension of 1 here. So if it is the case that x.shape at 1 is 1, then it's kind of like a spurious dimension. So we don't want to return a 3-dimensional tensor with a 1 here. We just want to return a 2-dimensional tensor exactly as we did before. So in this case, basically, we will just so that's what I expect to happen. And then one more thing I want to do here is, remember previously, all the way in the beginning, n was 3, and basically we're concatenating all the 3 characters that existed there. So we basically concatenated everything. And so sometimes that can create a spurious dimension of 1 here. So if it is the case that x.shape at 1 is 1, then it's kind of like a spurious dimension. So we don't want to return a 3-dimensional tensor with a 1 here. We just want to return a 2-dimensional tensor exactly as we did before. So in this case, basically, we will just say x equals x.squeeze. That is a PyTorch function. And squeeze takes a dimension that it either squeezes out all the dimensions of a tensor that are 1, or you can specify the exact dimension that you want to be squeezed. And again, I like to be as explicit as possible always, so I expect to squeeze out the first dimension only of this tensor, this 3-dimensional tensor. And if this dimension here is 1, then I just want to return b by c times n. And so self.out will be x, and then we
Okay. It's like if we are concatenating all the context vectors in one shot. So if in this case the n becomes like a 8, it becomes the previous case itself where we are stacking all of them one after the other. So it becomes an 80. So rather than having one more dimension, right, he's just flipping it around. So say this just for an example, this line is not there. Think of it 4 and just one example. This is 80. Now it is like 10 7 4 1, right? 1 4 7 10 is what you can see here. Okay, so if you can see here, right? Yeah, 1 4. Okay, so this 1 4 7 10 that you can see here, right? It will become an 80 size uh, array, only one element. So rather than having one more dimension, right, he is this whatever you see sleeps like this. So it will be 10 7 4 1. So in that way 80 size array is formed here. So this is just one dimension that will be sitting, so it will sleep like this on this line. So this will become a 4 cross 80 rather than 4 cross 1 cross 80. It is 4 cross 80. So we'll implement this. Self dot self comma n is the number of numbers that we want to concatenate, and equal to n. The three arrays that we will get, right? So basically it will be 4 cross 8 into 10. What we are saying is x dot view b. Okay, so it will concatenate as that many numbers. Okay, and if x dot shape 1 comes out to be 1, in that case, sorry, x dot squeeze across first dimension. Oh, sorry, I missed out on this. So
return self.out. So that's the candidate implementation. And of course, this should be self.in instead of just n. So let's run. And let's come here now and take it for a spin. So flatten consecutive. And in
That won't be n into block size, n underscore embedding, because we are not taking all of them, we are taking two. So we need to have that n number here, and that will do it as n into block size, comma hidden there.
the beginning, let's just use 8. So this should recover the previous behavior. So flatten
Okay.
consecutive of 8, which is the current block size. We can do this. That should recover the previous behavior. So we should be able to run the model. And here we can inspect. I have a little code snippet here where I iterate over all the layers. I print the name of this class and the shape. And so we see the shapes as we expect them after every single layer in its output. So now let's try to restructure it using our flattened consecutive and do it hierarchically. So in particular, we want to flatten consecutive not block size, but just 2. And then we want to process this with linear. Now the number of inputs to this linear will not be n embed times block size. It will now only be n embed times 2, 20.
Okay.
This goes through the first layer. And now we can, in principle, just copy paste this. Now the next linear layer should expect n hidden times 2. And
Oh, we are flattening the next layer as well. So whatever we output we got from the neurons, right? That was 4 cross 4 into 200. We are again flattening it, so it will become 4 cross 2 into 400. For examples, um, so here, right, 4 examples, 0, 1, 2, 3, each of size 200. That's the output from the layer 1. We are saying again again to flatten it by 2. By 2 means this 200, this 200. So this 200 will sit on top of this 0 as 200. So it will become a 400. So we'll have just two elements here, 400, 400. It's like 4 of them merged now into one.
The last piece of it.
If again we flatten it out, it will become 4, 1, and it will be 800. What we were getting before, right now we are getting in this way. So we'll have much more weights and everything in there.
Should expect an hidden times 2 again. So this is sort of like the naive version of it.
Because linear brings up its own weights and biases, so we will have much more number of weights and biases here. So flatten consecutive, this is 2, 2,
So running this,
oh sorry, we will have flatten consecutive as well, right? Yeah.
we now have a much, much bigger model. And we should be able to basically just forward the model. And now we can inspect the numbers in between.
So here if you see 4 cross 4 cross 10 is also, then again we are flattening, then we have just 2 elements and this 200 sit on top of 200, so it becomes 400. Then again flattening, 200 all sit on top of that, so 4 cross 400, and we are doing that flipping thing if the this index becomes ones, right? So 4 cross 200, then we are going through as linear, so 200 hidden layers, so 4 cross 200, batch norm 10h, and then the output, that is 4 cross 27.
So 4 by 20 was flattened consecutively into 4 by 4 by 20. This was projected into 4 by 4 by 200. And then batch norm just worked out of the box. And we have to verify that batch norm does the correct thing, even though it takes a 3-dimensional input instead of 2-dimensional input. Then we have 10h, which is element-wise. Then we crushed it again. So we flattened consecutively and batch norm 10h. And it squeezed out that dimension of 1. So we only ended up with 4 by 400. And then linear batch norm 10h and the last linear layer to get our logits. And so the logits end up in the same shape as they were before. But now we actually have a nice 3-layer neural net. And it basically corresponds to, it basically corresponds exactly to this network now, except only this piece here, because we only have 3 layers. Whereas here, in this example, there's 4 layers with a total receptive field size of 16 characters instead of just 8 characters. So the block size here is 16. So this piece of it is basically implemented here. Now we just have to kind of figure out some good channel numbers to use here. Now in particular, I changed the number of hidden units to be 68 in this architecture, because when I use 68, the number of parameters comes out to be 22,000. So that's exactly the same that we had before, and we have the same amount of capacity of this neural net in terms of the number of parameters. But the question is whether we are utilizing those parameters in a more efficient architecture. So what I did then is I got rid of a lot of the debugging cells here, and I reran the optimization. And scrolling down to the result, we see that we get the identical performance roughly. So our validation loss now is 2.029, and previously it was 2.027. So controlling for the number of parameters, changing from the flat to hierarchical, is not giving us anything yet. That said, there are two things to point out. Number one, we didn't really torture the architecture here very much. This is just my first guess. And there's a bunch of hyperparameter search that we could do in terms of how we allocate our budget of parameters to what layers. Number two, we still may have a bug inside the Bachelor 1D layer. So let's take a look at that, because it runs, but does it do the right thing? So I pulled up the layer inspector, sort of, that we have here, and printed out the shapes along the way. And currently it looks like the batch form is receiving an input that is 32 by 4 by 68, right? And here on the right, I have the current implementation of the batch norm that we have right now. Now, this batch norm assumed, in the way we wrote it, and at the time, that x is two-dimensional. So it was n by d, where n was the batch size. So that's why we only reduced the mean and the variance over the 0th dimension. But now x will basically become three-dimensional. So what's happening inside the batch norm layer right now, and how come it's working at all and not giving any errors? The reason for that is basically because everything broadcasts properly, but the batch norm is not doing what we want it to do.
It is broadcasting in the third dimension as well. So as a result, we now need to calculate. So for each of the neurons, we were calculating that. So we need to calculate across each of those pillars there, right?
So in particular, let's basically think through what's happening inside the batch norm, looking at what's happening here. I have the code here. So we're receiving an input of 32 by 4 by 68, and then we are doing here x.mean. Here I have e instead of x, but we're doing the mean over 0, and that's actually giving us 1 by 4 by 68. So we're doing the mean only over the very first dimension, and it's given us a mean and a variance that still maintain this dimension here. So these means are only taken over 32 numbers in the first dimension. And then when we perform this, everything broadcasts correctly still. But basically what ends up happening is, when we also look at the running mean, the shape of it, so I'm looking at the model.layers at 3, which is the first batch norm layer, and then looking at whatever the running mean became and its shape. The shape of this running mean now is 1 by 4 by 68, right? Instead of it being, just size of dimension, because we have 68 channels, we expect to have 68 means and variances that we're maintaining, but actually we have an array of 4 by 68. And so basically what this is telling us is this batch norm is currently working in parallel over
first
4
dimension.
times 68 instead of just 68 channels. So basically, we are maintaining statistics for every one of these 4 positions individually and independently. And instead, what we want to do is we want to treat this 4 as a batch dimension, just like the 0th dimension. So as far as the batch norm is concerned, it doesn't want to average, we don't want to average over 32 numbers. We want to now average over 32 times 4 numbers for every single one of these 68 channels. And so let me now remove this. It turns out that when you look at the documentation of torch.mean, so let's go to torch.mean. In one of its signatures, when we specify the dimension, we see that the dimension here is not just, it can be int, or it can also be a tuple of ints. So we can reduce over multiple integers at the same time, over multiple dimensions at the same time. So instead of just reducing over 0, we can pass in a tuple, 0, 1.
So the intention is for each of the 68 hidden neurons in the layer, right? We should have a mean. Okay, right? Because that's when that bell curve will be formed for each of the neurons. As a result, we should have mean for each of these. That's where only 68.
And here 0, 1 as well. And then what's going to happen is the output, of course, is going to be the same. But
now once the mean is calculated, it will be subtracted from all the elements and divided by the variances.
now what's going to happen is, because we reduce over 0 and 1, if we look at emean.shape, we see that now we've reduced, we took the mean over both the 0th and the 1st dimension. So we're just getting 68 numbers and a bunch of spurious dimensions here. So now this becomes 1 by 1 by 68, and the running mean and the running variance analogously will become 1 by 1 by 68. So even though there are the spurious dimensions, the correct thing will happen in that we are only maintaining means and variances for 68 channels. And we're now calculating the mean and variance across 32 times 4 dimensions. So that's exactly what we want. And let's change the implementation of batch norm 1D that we have so that it can take in 2-dimensional or 3-dimensional inputs and perform accordingly. So at the end of the day, the fix is relatively straightforward. Basically, the dimension we want to reduce over is either 0 or the tuple 0 and 1, depending on the dimensionality of x. So if x.ndim is 2, so it's a 2-dimensional tensor, then the dimension we want to reduce over is just the integer 0. And if x.ndim is 3, so it's a 3-dimensional tensor, then the dims we're going to assume are 0 and 1 that we want to reduce over. And then here we just pass in dim. And if the dimensionality of x is anything else, we'll now get an error, which is good. So that should be the fix. Now I want to point out one more thing. We're actually departing from the API of PyTorch here a little bit. Because when you come to batch norm 1D in PyTorch, you can scroll down and you can see that the input to this layer can either be n by c, where n is the batch size and c is the number of features or channels, or it actually does accept 3-dimensional inputs, but it expects it to be n by c by l, where l is, say, like the sequence length or something like that. So this is a problem because you see how c is nested here in the middle. And so when it gets 3-dimensional inputs, this batch norm layer will reduce over 0 and 2 instead of 0 and 1. So basically, PyTorch batch norm 1D layer assumes that C will always be the first dimension, whereas we assume here that C is the last dimension, and there are some number of batch dimensions beforehand. And so it expects n by C or n by C by L. We expect n by C or n by L by C. And so it's a deviation. I think it's okay. I prefer it this way, honestly, so this is the way that we will keep it for our purposes.
Okay, I already calculated result, so yeah. 0 and then 0 and its dimension.
So I redefined the layers, reinitialized the neural net, and did a single forward pass with a break just for one step. Looking at the shapes along the way, they're of course identical, all the shapes are the same, but the way we see that things are actually working as we want them to now is that when we look at the batch norm layer, the running mean shape is now 1 by 1 by 68. So we're only maintaining 68 means for every one of our channels, and we're treating both the 0th and the first dimension as a batch dimension, which is exactly what we want. So let me retrain the neural net now. Okay, so I retrained the neural net with the bug fix. We get a nice curve, and when we look at the validation performance, we do actually see a slight improvement. So we went from 2.029 to 2.022. So basically the bug inside the batch norm was holding us back like a little bit, it looks like. And we are getting a tiny improvement now, but it's not clear if this is statistically significant. And the reason we slightly expect an improvement is because we're not maintaining so many different means and variances that are only estimated using 32 numbers effectively. Now we are estimating them using 32 times 4 numbers. So you just have a lot more numbers that go into any one estimate of the mean and variance. And it allows things to be a bit more stable and less wiggly inside those estimates of.
Hmm. So we're just taking across one of the dimension. So we have many more means to calculate which was destabilizing it. Let me see.
Statistically significant. And the reason we slightly expect an improvement is because we're not maintaining so many different means and variances that are only estimated using 32.
Hmm. So because we're doing it across just one of the dimension, right? We had way more means to calculate from. Now when we crush it across two different dimensions, right, the number of mean we handle decreases. As a result, the fluctuations reduce a bit because number of
Two
means.
numbers effectively. Now we are estimating them using 32 times 4 numbers. So you just have a lot more numbers that go into any one estimate of the mean and variance. And it allows things to be a bit more stable and less wiggly inside those estimates of those statistics. So pretty nice. With this more general architecture in place, we are now set up to push the performance further by increasing the size of the network. So for example, I bumped up the number of embeddings to 24 instead of 10, and also increased the number of hidden units. But using the exact same architecture,
Not using sequential, is it? Okay. Oh, here I'm doing, but he's saying let's make it 24. Okay, says 27, no?
one estimating
And for
and tiny
each layer it
bucket
was
dimension,
showing the
which is exactly what we want.
for layer in layer dot under with 68 layers. Let's do it in the first instance. Embedding has out, no? How come it was working for 128 and it's not working here? Hmm. Because this run, that's why you were getting it, is it? Hmm. Got it. Now we should get it where it went. Unless you run this right, these are not getting initialized. These call functions are not getting called, so that's why you need to run that and then you need to get this. So let's make it 68 itself just to compare everything is fine. And then it should run. Oh. So 32 8 cross 10, then 32 4 cross 20, go 68. Flat and consecutive is where the problem is, that it's not getting crushed. Flat and consecutive किधर छे भाई? Start squeeze one, right? That's what was. But I'll just check. Yo. Okay. Now it should work. Now because we got one right, it got squeezed out and we are seeing that output. So now this should run, yeah.
So let me retrain the neural net now. You actually see a slight improvement. Almost holding out times for numbers. So you just have a lot more numbers that go into any one estimate of the mean and variance. And it allows things to be a bit more stable and less wiggly. With this more general architecture in place, we are now set up to push the performance further by increasing the size of the network. So for example, I bumped up the number of embeddings to 24 instead of 10, and also increased the number of hidden units. But using the exact same architecture, we now have 76,000 parameters, and the training takes a lot longer, but we do get a nice curve. And then when you actually evaluate the performance, we are now getting validation performance of 1.993. So we've crossed over the 2.0 sort of territory. Performance of 1.993. So we've crossed over the 2.0 sort of territory, and we're at about 1.99. But we are starting to have to wait quite a bit longer, and we're a little bit in the dark with respect to the correct setting of the hyperparameters here and the learning rates and so on, because the experiments are starting to take longer to train. And so we are missing sort of like an experimental harness on which we could run a number of experiments and really tune this architecture very well. So I'd like to conclude now with a few notes. We basically improved our performance from a starting of 2.1 down to 1.9, but I don't want that to be the focus because honestly, we're kind of in the dark, we have no experimental harness, we're just guessing and checking, and this whole thing is terrible. We're just looking at the training loss. Normally, you want to look at both the training and the validation loss together. The whole thing looks different if you're actually trying to squeeze out numbers. That said, we did implement this architecture from the WaveNet paper, but we did not implement this specific forward passive fit where you have a more complicated linear layer sort of, that is this gated linear layer kind of, and there's residual connections and skip connections and so on, so we did not implement that. We just implemented this structure. I would like to briefly hint or preview how what we've done here relates to convolutional neural networks as used in the WaveNet paper. And basically the use of convolutions is strictly for efficiency. It doesn't actually change the model we've implemented. So here, for example, let me look at a specific name to work with an example. So there's a name in our training set, and it's DeAndre, and it has 7 letters, so that is 8 independent examples in our model. So all these rows here are independent examples of DeAndre. Now, you can forward, of course, any one of these rows independently. So I can take my model and call it on any individual index. Notice, by the way, here, I'm being a little bit tricky. The reason for this is that extra at 7.shape is just one-dimensional array of 8. So you can't actually call the model on it. You're going to get an error because there's no batch dimension. So when you do extra at list of 7, then the shape of this becomes 1/8. So I get an extra batch dimension of 1, and then we can forward the model. So that forwards a single example. And you might imagine that you actually may want to forward all of these 8 at the same time. So pre-allocating some memory and then doing a for loop 8 times and forwarding all of those 8 here will give us all the logits in all these different cases. Now for us with the model, as we've implemented it right now, this is 8 independent calls to our model. But what convolutions allow you to do is it allows you to basically slide this model efficiently over the input sequence. And so this for loop can be done not outside in Python, but inside of kernels in CUDA. And so this for loop gets hidden into the convolution. So the convolution basically, you can think of it as it's a for loop applying a little linear filter over space of some input sequence. And in our case, the space we're interested in is one-dimensional, and we're interested in sliding these filters over the input data. So this diagram actually is fairly good as well. Basically what we've done is here they are highlighting in black one single sort of like tree of this calculation. So just calculating the single output example here. And so this is basically what we've implemented here. We've implemented this black structure. We've implemented that and calculated a single output, like a single example. But what convolutions allow you to do is it allows you to take this black structure and kind of like slide it over the input sequence here and calculate all of these orange outputs at the same time. Or here, that corresponds to calculating all of these outputs of at all the positions of DeAndre at the same time. And the reason that this is much more efficient is because, number one, as I mentioned, the for loop is inside the CUDA kernels in the sliding, so that makes it efficient. But number two, notice the variable reuse here. For example, if we look at this circle, this node here is the right child of this node, but it's also the left child of the node here. And so basically this node and its value is used twice. And so right now, in this naive way, we'd have to recalculate it. But here we are allowed to reuse it. So in the convolutional neural network, you think of these linear layers that we have up above as filters. And we take these filters, and they're linear filters, and you slide them over input sequence, and we calculate the first layer, and then the second layer, and then the third layer, and then the output layer of the sandwich. And it's all done very efficiently using these convolutions. So we're going to cover that in a future video. The second thing I hope you took away from this video is you've seen me basically implement all of these layer Lego building blocks or module building blocks. And I'm implementing them over here. And we've implemented a number of layers together. And we've also implementing these containers. And we've overall PyTorchified our code quite a bit more. Now, basically what we're doing here is we're re-implementing torch.nn, which is the neural network's library on top of torch.tensor. And it looks very much like this, except it is much better because it's in PyTorch instead of jankling my Jupyter notebook. So I think going forward, I will probably have considered us having unlocked torch.nn. We understand roughly what's in there, how these modules work, how they're nested, and what they're doing on top of torch.tensor. So hopefully we'll just switch over and continue and start using torch.nn directly. The next thing I hope you got a bit of a sense of is what the development process of building deep neural networks looks like, which I think was relatively representative to some extent. So number one, we are spending a lot of time in the documentation page of PyTorch, and we're reading through all the layers, looking at the documentations, what are the shapes of the inputs, what can they be, what does the layer do, and so on. Unfortunately, I have to say the PyTorch documentation is not very good. They spend a ton of time on hardcore engineering of all kinds of distributed primitives, etc. But as far as I can tell, no one is maintaining documentation. It will lie to you. It will be wrong. It will be incomplete. It will be unclear. So unfortunately, it is what it is, and you just kind of do your best with what they've given us. Number two, the other thing that I hope you got a sense of is there's a ton of trying to make the shapes work. And there's a lot of gymnastics around these multidimensional arrays. And are they two-dimensional, three-dimensional, four-dimensional? What layers take what shapes? Is it NCL or NLC? And you're permuting and viewing, and it just can get pretty messy. And so that brings me to number three. I very often prototype these layers and implementations in Jupyter notebooks and make sure that all the shapes work out. And I'm spending a lot of time basically babysitting the shapes and making sure everything is correct. And then once I'm satisfied with the functionality in a Jupyter notebook, I will take that code and copy paste it into my repository of actual code that I'm training with. And so then I'm working with VS Code on the side. So I usually have Jupyter notebook and VS Code. I develop in Jupyter notebook, I paste into VS Code, and then I kick off experiments from the repo, of course, from the code repository. So that's roughly some notes on the development process of working with neural nets. Lastly, I think this lecture unlocks a lot of potential further lectures because number one, we have to convert our neural network to actually use these dilated causal convolutional layers, so implementing the ComNet. Number two, potentially starting to get into what this means, what are residual connections and skip connections, and why are they useful. Number three, as I mentioned, we don't have any experimental harness. So right now I'm just guess and checking everything. This is not representative of typical deep learning workflows. You have to set up your evaluation harness. You can kick off experiments. You have lots of arguments that your script can take. You're kicking off a lot of experimentation. You're looking at a lot of plots of training and validation losses, and you're looking at what is working and what is not working. And you're working on this like population level, and you're doing all these hyperparameter searches. And so we've done none of that so far. So how to set that up and how to make it good, I think is a whole another topic. And number three, we should probably cover recurrent neural networks, RNNs, LSTMs, grooves, and of course transformers. So many places to go, and we'll cover that in the future. For now, bye. Sorry, I forgot to say that if you are interested, I think it is kind of interesting to try to beat this number 1.993, because I really haven't tried a lot of experimentation here, and there's quite a bit of low-hanging fruit potentially to still push this further. So I haven't tried any other ways of allocating these channels in this neural net. Maybe the number of dimensions for the embedding is all wrong. Maybe it's possible to actually take the original network with just one hidden layer and make it big enough and actually beat my fancy hierarchical network. It's not obvious. That would be kind of embarrassing if this did not do better, even once you torture it a little bit. Maybe you can read the WaveNet paper and try to figure out how some of these layers work and implement them yourselves using what we have. And of course, you can always tune some of the initialization or some of the optimization and see if you can improve it that way. So I'd be curious if people can come up with some ways to beat this. And yeah, that's it for now. Bye.
One thing I would like to the
But
16 didn't get
it's much more efficient. Okay? And so in black is filters equal loops hidden convolution as allocating all of the, or just look at trying to squeeze in that paper where you have a more complicated linear residual connections and skip connections and so on. So we did not implement that. We just implemented this structure. I would like to briefly hint or preview how what we've done here relates to convolutional neural networks as used in the WaveNet paper. And basically the use of convolutions is strictly for efficiency. It doesn't actually change the model we've implemented. So here, for example, let me look at a specific name to work with an example. So there's a name in our training set and it's DeAndre. And it has 7 letters, so that is 8 independent examples in our model. So all these rows here are independent examples of DeAndre. Now, you can forward, of course, any one of these rows independently. So I can take my model and call it on any individual index. Notice, by the way, here, I'm being a little bit tricky. The reason for this is that extra at 7. So you can't actually call the model on it when you do extra at batch dimension of 1, and then we can forward the model. So that forwards a single example. And you might imagine that you actually may want to forward all of these 8 at the same time. So pre-allocating some memory and then doing a for loop 8 times and forwarding all of those 8 here will give us all the logits in all these different cases. Now for us with the model, as we've implemented it right now, this is 8 independent calls to our model. But what convolutions allow you to do is it allow you to basically slide this model efficiently over the input sequence.
Yeah.
And so this for loop can be done not outside in Python, but inside of kernels in CUDA. And so this for loop gets hidden into the convolution. So the convolution basically, you can think of it as it's a for loop applying a
Allows us to forward lean.
little linear filter over space of some input sequence. And in our case, the space we're interested in is one-dimensional, and we're interested in sliding these filters over the input data. So this diagram actually is fairly good as well. Basically what we've done is, here they are highlighting in black one single sort of like tree of this calculation. So just calculating the single output example here. And so this is basically what we've implemented here. We've implemented this black structure, we've implemented that and calculated a single output, like a single example. But what convolutions allow you to do is it allows you to take this black structure and kind of like slide it over the input sequence here and calculate all of these orange outputs at the same time.
Means he's talking about this for loop rather than calculating just one, right? Here, just for one example, what will be the output? He's saying in a batch of all the numbers, it will calculate it. So here, like for 8 of them, right, will efficiently calculate this logits.
Or here, that corresponds to calculating all of these outputs of at all the positions of DeAndre at the same time. And the reason that this is much more efficient is because, number one, as I mentioned, the for loop is inside the CUDA kernels in the sliding, so that makes it efficient. But number two, notice the variable reuse here. For example, if we look at this circle, this node here is the right child of this node, but it's also the left child of the node here. And so basically this node and its value is used twice. And so right now, in this naive way, we'd have to recalculate it. But here we are allowed to reuse it. So in the convolutional neural network, you think of these linear layers that we have up above as filters. And we take these filters, and they're linear filters, and you slide them over input sequence, and we calculate the first layer, and then the second layer, and then the third layer, and then the output layer of the sandwich. And it's all done very efficiently using these convolutions. So we're going to cover that in a future video. The second thing I hope you took away from this video is
That was it. Bye everyone.